Thanks to CuriosityStream for sponsoring this video. Watch thousands of documentaries and get access to Nebula for free when you sign up using the link in the description. Bernoulli's equation is a simple but incredibly important equation in physics and engineering that can help us understand a lot about the flow of fluids in the world around us. It essentially describes the relationship between the pressure, velocity, and elevation of a flowing fluid. It has countless applications. We can use it to explain how planes generate lift, or to calculate how fast liquid will drain from a container, for example. We'll explore these applications and a few more later on, but let's start by reviewing the equation itself. It was first published by the Swiss physicist Daniel Bernoulli in 1738, and it looks like this. The equation states that the sum of these three terms remains constant along a streamline. Each of the terms is a pressure. The first term is the static pressure, which is just the pressure P of the fluid. Then we have the dynamic pressure, which is a function of the fluid density, ρ, and velocity, v, and represents the fluid kinetic energy per unit volume. And the last term is the hydrostatic pressure, which is the pressure exerted by the fluid due to gravity. G is gravitational acceleration, and h is the elevation of the fluid, which is just its height above a reference level. This is the pressure form of the equation, but it can also be presented in the head form and the energy form. We can think of Bernoulli's equation as a statement of the conservation of energy. It says that along a streamline, the sum of the pressure energy, kinetic energy, and potential energy remains constant. This is really valuable information that can help us analyze a whole range of fluid flow problems. The equation does have a few limitations, which I'll cover later on in the video. But for now, the important thing to note is that it can only be applied along a streamline. We can define a streamline in steady flow as the path traced by a single particle within the fluid, or more technically, as a curve that at all points is tangent to the particle velocity vector. Let's look at an example where we apply Bernoulli's equation to flow through a pipe which has a change in diameter. We want to use the equation to see how the pressure changes as the flow passes from the larger to the smaller diameter. Bernoulli's equation is usually used to compare the flow at two different locations, so we can rewrite it like this, with points 1 and 2 both being on the same streamline. There's no significant change in elevation between points 1 and 2, so the potential energy terms cancel each other out. And if we put all of the static pressure terms on one side, we get this equation for the change in pressure. If we assume that the fluid is incompressible, the mass flow rate at points 1 and 2 must be equal. This gives us what's called the continuity equation, which is just a statement of the conservation of mass. Mass flow rate is equal to the product of the fluid density, the pipe cross-sectional area, and the fluid velocity. So we can rearrange the continuity equation to obtain an equation for the velocity at point 2. The cross-sectional area, A2, is smaller than A1, which means that the velocity of the flow increases as it passes into the smaller diameter pipe. This is quite intuitive. By substituting this equation for V2 into Bernoulli's equation, we can see that since the velocity increases between points 1 and 2, the pressure between both points must decrease. This concept that for horizontal flow an increase in fluid velocity must be accompanied by a decrease in pressure is one way of formulating what we call Bernoullis Principle. It can seem counterintuitive because people often expect an increase in velocity to result in a corresponding increase in pressure, but it makes sense if we think about the conservation of energy. The energy required to increase the fluid velocity comes at the expense of the static pressure energy. Bernoulli's principle shows up in a lot of different places. We can use it to help explain how plane wings generate lift. Fluid flowing over an airfoil travels faster than fluid flowing below it. According to Bernoulli's principle, this creates an area of low pressure above the airfoil and an area of high pressure below it. And it's this pressure difference that generates lift. I'll cover lift and drag forces in more detail in a separate video. Bernoulli's principle also explains how Bunsen burners work. When the gas valve is opened, gas flows into the barrel at high velocity. Following Bernoulli's principle, this high velocity creates an area of low pressure in the barrel, which draws air in through the air regulator, allowing for more complete combustion of the gas. Several different flow measurement devices rely on Bernoulli's equation to determine the velocity of a flowing fluid. The Pitostatic Tube is one such device. It's often used in aircraft to measure airspeed. Here's how it works. If we place a tube into a flowing fluid, like this, and we attach a pressure meter to the end of it, the meter will measure the pressure at the end of the tube. At this point, the fluid velocity is reduced to zero, so it's called the stagnation point, and the pressure measured by the meter is called the stagnation pressure. We can apply Bernoulli's equation between an upstream point and the stagnation point, and show that the stagnation pressure is equal to the sum of the static pressure and the dynamic pressure terms. All of the kinetic energy is essentially being converted into pressure energy at the stagnation point. If we add an outer tube which is sealed at the end but has holes further downstream, the outer tube will measure the static pressure of the fluid instead of the stagnation pressure. These two pressure measurements give us all of the information we need to determine the velocity of the flow. Another flow measurement device that uses Bernoulli's equation is the Venturi Meter, which is an instrument used to determine the flow rate through a pipe. It works by measuring the pressure drop across a converging section of pipe. Say we want to determine the flow rate, Q, which is the velocity multiplied by the pipe cross-sectional area at point 1. We can easily rearrange the pressure drop equation we derived earlier when we looked at a change in diameter to get this equation for flow rate. All we need to know is the dimensions of the Venturi meter, the fluid density, and the pressures P1 and P2, and that allows us to calculate the flow rate. The Venturi meter has no moving parts and is a very simple and reliable way of measuring the flow rate through a pipe. The diverging section is longer than the converging section to reduce the likelihood of flow separation and keep energy losses low. Let's look at one more example where we can apply Bernoulli's equation. Say we have a beer keg, and we want to calculate how fast beer will drain when we first open the tap at the bottom. All we need to do is define our 2 points along a streamline and apply Bernoulli's equation. It's a gravity-fed keg with a vent at the top, meaning that it's not pressurized. The pressure at both points will be atmospheric, and so the static pressure terms cancel each other out. We can also assume that the keg is large enough that the fluid velocity at point 1 is close to zero. If we rearrange Bernoulli's equation and define the height between the beer level and the tap as h, we get this equation for the beer velocity out of the tap. Those were a few examples of cases where we can apply Bernoulli's equation to get some valuable information or to solve a problem. But to use it correctly, it's important to have an understanding of the limitations of the equation, which arise because of how it's derived. There are several different ways Bernoulli's equation can be derived. It can be derived based on conservation of energy, by considering that the work done on the fluid increases its kinetic energy. Or it can be derived by applying Newton's second law, which involves determining the forces acting on a fluid particle and applying F equals ma. Although I won't cover either derivation here, they do both make some assumptions that we need to be aware of, since they limit how we can apply the equation. Firstly, the derivation of Bernoulli's equation assumes that flow is laminar and that it is steady, meaning that it doesn't vary with time, like this. Next, it assumes that the flow is inviscid, meaning that shear forces due to fluid viscosity are negligible. This assumption is needed because viscosity would result in a dissipation of some of the fluid's internal energy, and so the idea that energy is conserved along a streamline would no longer apply. And finally, the derivation of Bernoulli's equation assumes that the fluid behaves as if it's incompressible. This is usually valid for liquids, but might not be for gases at high velocities. All three of these assumptions need to be valid if you want to apply Bernoulli's equation. Adapted versions of the equation which can be applied to unsteady and compressible flows do exist, although they're a bit more complicated. Being able to recognize when Bernoulli's principle is at play, or when Bernoulli's equation can be applied to solve a problem, is a powerful tool in any engineer's arsenal. If you'd like to see a few more real-world examples of Bernoulli's principle in action, you can check out the extended version of this video on Nebula. Nebula is a video streaming service built entirely by educational creators like myself. It's home to some of the best creators out there, including Real Engineering, Practical Engineering, and City Beautiful. So you can watch content from them and many others on Nebula, completely ad-free. All of my videos are on Nebula, without any ads, and in the version of this video on Nebula, I've replaced this sponsorship message with a few more really interesting examples of Bernoulli's principle. Then there's the growing catalog of exclusive Nebula originals that you won't be able to watch anywhere else, like Mustard's fascinating look at Imperial Japan's underwater aircraft carriers, or the logistics of D-Day series. And best of all, you can get access to Nebula for free when you sign up to CuriosityStream using the link in the description. CuriosityStream is the streaming service for high-quality documentaries. It has a catalog of thousands of incredible titles, covering engineering, science, history, and more. So whether you want to learn about the pioneers of aviation and colonization of the moon, or discover the secrets of the deep ocean with narration by David Attenborough, CuriosityStream is the place to do it. If you sign up to CuriosityStream using this link and the promo code EfficientEngineer, you'll get a 26% discount on the annual plan, and you'll get Nebula for free, all for just $14.79. So to take advantage of this incredible deal, head over to curiositystream.com/EfficientEngineer, or click on the link in the description and use the code EfficientEngineer. You'll be supporting not only this channel, but a load of other creators in the educational community as well. And that's it for this introduction to Bernoulli's equation. Thanks for watching.